It is not at all uncommon to want to understand the variability, or more specifically, the variance within a population. And when we're trying to understand the variance within a population, more than just a point estimate for the variance, we might want a confidence interval for the variance. This would allow us to understand in the population how much variability is there really within whatever trait it is that we're measuring. And so in order to do this, what we need to be able to do is extend the ideas of confidence intervals to the case of variances. Now, in order to actually do this, we would need to be able to figure out the sampling distribution of the variance. Unfortunately, the sampling distribution for the variance isn't going to be as straightforward as, for instance, getting to appeal to the central limit theorem. But what we can do is we can investigate what happens when we have normally distributed data. And in particular, if we have normally distributed data, then the variance is going to follow sort of a modified chi-squared distribution. And because of this, we can use that result in order to form confidence intervals for the variance in these populations. So first, we need to look at what is the sampling distribution for the variance. If we assume that x1 through xn are drawn from any population, and this is a population with a mean of mu and a variance of sigma squared, then the sample variance is given by s squared. It's the notation we use, and it's 1 divided by n minus 1, and then we take the sum of these squared deviations. So it's the sum of xi minus the sample mean, all of that squared. Okay. If we have our estimator here, we know that it's going to be an unbiased estimator for the population variance, no matter what we're assuming about the population. However, if we're willing to assume that the population is normally distributed, then we have this modified version of s squared, right? So we take s squared, we multiply it by our sample size minus 1, and we divide by the true value. Then what this is going to give us is a chi-squared n minus 1 distribution, right? And so here, this gives us a result that is quite similar to results that we maybe have seen for the mean, where we might be looking at, for instance, say, x bar minus the true mean over sigma divided by the square root of n, right? This can follow a normal 0, 1. Okay, and this result that we have for the variance is quite similar, right? It is a value that ends up giving us a chi-squared distribution, and it's a chi-squared distribution with n minus 1 degrees of freedom in it. Okay, so the chi-squared distribution with n minus 1 degrees of freedoms. Now we can use this result to form a confidence interval using the standard way that you can derive confidence intervals in this situation, right? So you can end up taking this as the sampling distribution and then solving for what the interval is going to have to be. So what does that actually end up looking like? Well, a 100 times 1 minus alpha % confidence interval for the normal variance is going to be given by this expression here, right? So what we have is we have n minus 1 times s squared, right? And then we divide by x, or chi-squared of n minus 1, 1 minus alpha over 2. So this is a critical value from the chi-squared distribution. And then for the upper bound, we're going to have n minus 1 times s squared, divide by a critical value from the chi-squared distribution. Okay. Now, the important thing that we'll highlight here is that these two critical values are not going to be the same thing, right? If these critical values were the same, then the lower bound and the upper bound would be exactly the same as one another. And so these are actually going to be different critical values. And because of that, it sort of does not take the form that is quite common for confidence intervals, right? We often have something like x bar plus or minus our critical value, say z alpha over 2, times by the standard error of x bar, right? This is a very common format. The interval that we have here does not actually follow this format. And so because of that, it sort of is working in a different paradigm a little bit. So the values of chi-squared n minus 1, 1 minus alpha over 2, and chi-squared n minus 1 alpha over 2 are the critical values, and it's from the chi-squared n minus 1 distribution. Okay, and so specifically, they're defined in exactly the same way as any critical values are going to be defined, right? So if we take f to be the cumulative distribution function for the chi-squared n minus 1 distribution, then if you plug in the critical value at 1 minus alpha over 2, that gives us 1 minus alpha over 2. And if you plug in the critical value of alpha over 2, that's going to give us alpha over 2, right? So the critical values are defined in the exact same way. However, they're coming from a chi-square distribution rather than from a normal distribution or a t-distribution or something similar. Okay? N still refers to our sample size. And the reason that we need these different critical values is because the chi-square distribution is not actually symmetric, right? So instead of it looking something like our bell curve for our normal and our t and similar distributions, the chi-square distribution is actually typically going to look sort of long-tailed, right? It's going to look something more like this, okay? And so because of that, we actually can't take them to be symmetric values. And so really what we're saying there is that if we wanted to put, say, alpha over 2 down in this smaller tail here, right? We take alpha over 2 here, and we take alpha over 2 up in the positive tail over here, right? These aren't symmetric values. They're not going to be equal to the negatives of one another. So they're fundamentally different values. And so that's why we need to hold on to both of them in this interval here. Right, so the chi-squared n minus 1 minus alpha over 2 is not equal to negative 1 times chi-squared n minus 1 of alpha over 2. This does hold when they're normally distributed or when they're t-distributed or when they have any symmetric distribution, but it doesn't hold in this case. Okay, and so we actually need both critical values holding out there. So we can take a look at how this works out in an example here. So we're estimating or a researcher wants to estimate the population variance of systolic blood pressure measurements from some specific population. The random sample of 36 individuals is taken, and their blood pressure is actually measured with a sample variance of 120. Okay, blood pressure measurements are assumed to be normally distributed. Okay, and so because they're assumed to be normally distributed, we can use the standard interval for our normal-based variances here. We want a 95% confidence interval, right? And so then we can think about, well, what do we need? And the pieces of information that we need, right? So the first is we want to find s squared, and we know that s squared is given to us by 120. The second piece is that we're going to need our value of n, and n is told to be 36, okay? We want to work out that alpha is equal to 1 minus 0.95, right, which is going to give us 0.05. Okay. And then in this case, we need two critical values, right? We're going to need the chi-squared critical value where we take alpha over 2. So that's going to give us a 0.025. And they're always going to be coming from the chi-squared n minus 1 distribution. So n minus 1 is 35, right? So that's going to be the chi-squared 35. The first critical value is going to be 0.025. Okay. But we're also going to need the chi-squared 35 and then 1 minus alpha over 2. And so 1 minus alpha over 2 in this case is 0.975. Right, where this is 1 minus 0.05 divided by 2, okay? And so in this case, we need both of these critical values here, right, which we can get using, for instance, the R programming language, right? And so we can start pulling out all of this information here, okay? So the normal population means that we can proceed using these variance, or the intervals for the variance here. We're given that n is 36 and s squared is 120. The critical values for 0.05, right, as alpha, so we need chi-squared n minus 1 at 1 minus alpha over 2, and we can get that as 53.20035, okay? And we also need chi-squared of n minus 1 at alpha over 2, which is 0.025, which gives us 20.56938 and change, right? And so in this case, we can see that these are not going to be sort of symmetric critical values, right? If we actually want to get them, we can use R, and in R, we can call the Q chi-square function, right? And so in this case, the Q is standing for the fact that we want the quantile, right? So Q is for the quantile here. And then the chi-square tells us that we want the chi-square distribution. Okay, and again, we provide two different parameters for it. So the first parameter is going to be alpha, and then the second parameter is going to be the number of degrees of freedom, which in our case is 35. Right, so 0.975, 35 is going to give us this 53 and change. 0.025 and 35 is going to give us this 20.56 and change. Okay, and so then using all of these values, we can plug into the formula that we actually need for our confidence interval, right? So plugging in, we're going to take the formula n minus 1 times our sample variance, divide by the upper critical value, n minus 1 times our sample variance, divide by the lower critical value. So 35 times 120 over 53, 35 times 120 over 20.57. And all of this gives us 78.95 to 204.19. Okay, and so our confidence interval for the variance in this case is going to fall between 78.95 and 204.19. Now, that's how we can do confidence intervals for the variance, but sometimes we're going to be more interested in using the standard deviation as the measure of uncertainty. And so what can we do in these cases? Well, we know that the standard deviation is given by the square root of the variance, right? So if we want to find the standard deviation of any random quantity, then we take that to be the square root of the variance of that quantity. Okay, and because it's this sort of straightforward transformation, we can actually use that fact to find approximate confidence intervals for the standard deviation. So we know that sigma is the square root of sigma squared, and in the sample, it's s is the square root of s squared, right? And so to form approximate intervals, all we're going to have to do is transform the intervals that we have for the variance. So in particular, if we have L to U is an interval for sigma squared, then the square root of L to the square root of U is going to be an approximate interval for sigma. And so in normal populations, what this means is that we can take the standard confidence interval that we have, right? So we had n minus 1 s squared over the critical value from the chi-squared, n minus 1 s squared times the other critical value from the chi-squared. And if we square root that entire thing, right? So square root the lower bound, square root the upper bound, then that's going to give us an approximate confidence interval. Now, because we have s squared in here, we can pull this out with just the sample standard deviation out front, and that's going to give us another way of expressing exactly the same interval. So all we've done here is we've said, well, we have a valid interval for the variance. What happens if we just square root this interval? And that's going to be a common way of getting the confidence interval for the standard deviation. Now, this would also apply to any transformation of any parameter. And so in particular, let's say that we wanted to find a interval for, say, mu squared, right? Then if we have AB is an interval for mu, right, then we can take A squared, B squared, for instance. Okay, and so this is going to apply far more broadly than just for the standard deviation and the variance. However, it is important to keep in mind that it's actually only going to give us approximate confidence intervals, right? It's not going to give us full confidence intervals or fully valid, it's going to give us approximate. So if we turn back to that exact example we were working on before, what can we do in this case? Well, again, we have all of the same information, right? N is 36, the variance is 120. We want a 95% confidence interval for the standard deviation in this case. Okay, so as before, because it's normal population, the process can proceed. We're given all of the same information, and so it's sort of just summarized here. And so we could plug directly into this formula, right? And so we take the formula with the square roots. We end up taking the square root of 35, 120 over 53, and the square root of 35 times 120 over 20, and that gives us 8.89 times, or up to 14.29. And so if we want a confidence interval for the standard deviation in this case, that confidence interval is given by this 8.89 to 14.29. The other thing that we could have done here is that because in the first part we actually found the interval for sigma squared to be 78.95 to 204.19, then the interval for sigma is going to be the square root of these endpoints, right? So we take the square root of 78.95, we take the square root of 204.19, and that gives us exactly the same thing. So if you've already found the interval for the variance, you don't actually have to use the full formula. You can just take the square root of the values that you've already found. Again, this is an approximate interval, but it's going to work in much the same way, right? So in normal populations, we can find asymmetric confidence intervals, right? Because we're using the chi-squared distribution here. We're not using a symmetric distribution. So they're going to be asymmetric confidence intervals for the variance and for the standard deviation by using those transformations based off of that chi-squared sampling distribution, right? This is going to be one way that we can end up conducting some statistical inference about the variance. It allows us to understand the variability of a population and to estimate what's actually going on within it. The process of finding the confidence interval follows in much the same way as finding any confidence interval. The really only tricky part about doing this is that that chi-square distribution is a lot less nicely behaved than the normal distribution, and so we have to be a little bit more cautious when we're thinking about the critical values that we're actually using. But otherwise, as soon as we know we're working with a normal population, we know that these confidence intervals are going to be valid, and then we can work through the mechanics of working out what that confidence interval is, and then use that for whatever purpose we're trying to do for the statistical inference we're trying to conduct.